it's time for part 2 of Volumes of Rotational Solids. So we did this last time, we did the disk method. Remember with the disk method, this is used when the solid contains no hollow parts. But with the washer method, which we're going to do today, the washer method, this is going to be used when there are hollow parts. So the reason it's called a washer method is because this is an example of a washer, right? You use it when you're fastening things. And if I was to rotate this, again, I'm not very good at picturing these things, but if I was to rotate this, see what you'd get? You get like a sphere with a big hole in the middle. You get a sphere within a sphere, wouldn't you? With the inner sphere being an empty circle. So in that case, you can't use the disk method. You'd have to use the washer method. Here's how it works. You actually have 2 radii of rotation this time. Last time we had the 1 radius of rotation, now you have 2. One's going to be the outer radius, which you usually designate with a capital R, and this is from the axis of rotation to the outside edge of the area being rotated. So this is exactly the same as the radius of rotation we used before. But now you're also going to have an inner radius, and this is from the axis of rotation to the inner edge. Alright, so I'm going to explain that more when we draw our pictures down here and everything. Let's just get all the formulas and everything down, and then we'll go from there. By the way, if you can maybe picture this, how this is going to work is in order to get the volume, you're going to get the volume of the solid, including the hole. You're going to subtract the volume of the hole. So what that will leave you with is the volume of the solid part, not including the hole, and that's exactly what we want. So here you go, here's your formulas. If your plane region is being revolved around the x-axis, you get this formula. V equals pi, just like last time, a to b, and then you're going to have fx squared minus g of x squared in terms of x. You're going to integrate there, right? So the f function is going to be that volume of the solid including the hole, and the g of x function is going to be the volume of just the hole. Subtract those, you're left with the volume of the solid itself. And in this case, you would write the equations in terms of x. That is, after all, why you have this x here and this x here. It's showing you're writing your functions in terms of x. If you revolve your plane region around the y-axis, you get v equals pi, integrate from a to b. This time it's going to be f of y squared minus g of y squared. And this is in terms of y when you integrate this time. So of course we're going to write the equations in terms of y. Okay? And that's it. So let's try a couple of these. Consider the area bounded by the graphs y equals negative x squared plus 2x plus 1 and y equals 1. What volume is generated if this area is rotated about the x-axis? Okay, so let's do a little sketch here. We're rotating it around the x-axis, so this is our axis of rotation right here. Maybe I'll even label that to make sure we're clear. Axis of rotation. And it's going to be bounded by the line y equals 1. So maybe I'll just put that line in there as well. The y equals 1 line. Something like that. Okay, well, let's see for this quadratic, it's obviously going to be a parabola. I could, since y is equal to this and y is also equal to 1, I could state that this negative x squared plus 2x plus 1, let's make that equal to 1. And then we'll solve from there. So let's see, I could move the 1 over, and I'd have negative x squared plus 2x, that cancels, equals 0. The 1's just cancel out. I could take out a negative x, or a positive x, but I'll take out negative x. Negative x times what equals negative x squared? X. Negative x times what equals positive 2x? Negative 2 equals 0. So x is either equal to 2, or x is equal to 0. And remember, this is when y is equal to 1. So our 2 points we could graph here are 0, 1, and 2, 1. Let's put those on our graph. So here's 1, here's 2, and our 2 points are 0, 1, which is right here, and 2, 1, which is right here. Okay, nice. Well, look, if this is a parabola, and it is, it's quadratic, and if we have the same y value here, then our vertex must be right in the middle, right? Because of symmetry, it must be right in the middle. So to get our vertex, we can just plug 1 into this equation right here, and it'll give us the vertex. That's what I'm going to do now. This isn't the only way you could do this, by the way. There's different ways you could do this. You could complete the square or something like that. So our vertex is going to be at 1 comma something. How do we figure it out? We plug 1 in here. So we get y equals negative 1 squared is still 1 plus 2 times 1 is 2 plus 1. So y equals negative 1 plus 2 is 1 plus another 1 is 2. Our vertex is at 1, 2. Oh, this worked out very nicely. We have our vertex right here, which means our parabola looks like this. Of course, it keeps going down, but I'm not going to draw that. And this, and it keeps going, but I'm not going to draw that. So this in here is what we're interested in. And what we're going to do is we're going to take this piece here and we're going to rotate it around this axis of rotation here. So can you picture this? It's going to kind of be a sphere, but you're going to have this big space in the middle. This is why you cannot use the disk method, because you got a space, you got a hollow piece right here. When you rotate, this is all going to be hollow in there. So there's two things we need. We need the outer radius, which is from the axis of rotation to the outside edge. So let's see. Here's my axis of rotation. We got it labeled right here. And my outer edge is anywhere you want along here. So I'll just draw it from here up to there. Remember, it doesn't matter if you draw it here or there, even though they're different lengths, because we're going to come up with a function that explains it, not an actual constant amount. So that's my big R. That's the same radius of rotation we used last time. But the new one we have to use is from the axis of rotation to the inner edge. And that would be from here to here. This would be your small r right there. Now, one thing to notice about this distance, this small r, do you see that wherever I draw it this time, it's exactly the same? How big is that small r distance, that inner radius? It's just 1. Our small r is actually going to be equal to 1. All right, we're rotating around the x-axis, so we're going to use the top formula right here. I'm going to cheat, and I'm just going to copy-paste it here. And away we go. Volume equals pi. Okay, what are our bounds? Well, we're going from 0, this part that's being rotated is being rotated from 0 all the way up to 2. So those are our lower and upper bounds, 0 and 2. By the way, I'm just going to add something here. These f functions here, these are the r value, right? That's the function that represents that outer radius, capital R, and the g functions, these are the small r. These are the functions that represent the inner radius. So for the next bit here, we want our function for the outer function. That's this function here. Well, wait a minute. That's just the parabola. We just need the equation of the parabola, which is right here. Negative x squared plus 2x plus 1. So that is what we're going to write here. Negative x squared plus 2x plus 1. And we have to square all that. Oh boy. Minus. Okay, now this is good news. For our g of x, that is the little r function. And as I already said, it stays the same. It's constant. That distance right there is always the same. It's always 1. So we only need to do 1 squared. So we'll do all that, and then we'll integrate in terms of x. So we're definitely going to have to simplify. We're not ready to integrate yet. So we got to square this. Kind of hard to do, but let's see if we can do it. We're going to multiply negative x squared times all of these, right? So negative x squared times negative x squared is positive x to the 4th. Negative x squared times positive 2x is negative 2x cubed. And negative x squared times positive 1 is negative x squared. Now I need to multiply 2x times all these. 2x times negative x squared is negative 2x cubed. 2x times itself is 4x squared. And 2x times 1 is 2x. Now I need to multiply 1 by all these things. So everything stays the same when you multiply by 1. Negative x squared plus 2x plus 1. And then we need to take away 1 squared, which is still 1. All right, let's combine our like terms here. So I think we only have one x to the fourth. X cubes, I see an x cubed here, and that's it. So negative 2 and negative 2 is negative 4x cubed. X squared, there's 1, there's 1, and there's 1. Negative x squared plus 4x squared is 3x squared. Take away 1x squared is 2x squared. X's, here's 1 and here's 1, so we have plus 4x. And nice, those cancel out. So this is what we have to integrate, and we can finally do that. So we've got pi, then x to the fifth and divide by the same number, minus 4x to the fourth and divide by the same number, plus 2x cubed and divide by the same number, plus 4x squared and divide by the same number. This is from 0 to 2. Okay, we can simplify a bit. What a question. X to the fifth over 5. The fourths cancel, so you just get minus x to the fourth. Nothing you can do here. And the 4 and the 2 cancel, or simplify, you get 2x squared from 2 to 0. Okay, the 0 is going to be nice, so, but the 2 is not so nice. 2 to the fifth power is 32 divided by 5, minus 2 to the fourth power is 16, plus 2 to the third power is 8 times 2 is another 16 over 3. 2 squared is 4 times 2 is 8. And then we're going to subtract. We're going to put 0 into all these. You're going to get 0 every single time. So that's not going to make a difference. V equals pi. I don't know. We've got this negative 16 and this positive 8, which gives us negative 8. And we got the 32 over 5 and the 16 over 3. So we need to get common denominators of 15. This is, of course, negative 8 over 1. So it's going to be over 15. Multiply by 15, you get negative 120. Multiply by 3, you get 96. And multiply by 5, you get 80. So if you add the 96 and 180 together, you get 176. Minus 120, you get 56. Times pi. So 56 pi over 15 is the exact volume of this shape when you rotate it around the x-axis. Okay, the second one, of course, we're going to rotate around the y-axis. So let's see if we can figure out what this looks like. Okay, it's bounded by the graphs y equals x over 2 and y equals root x. Let's go out to 4 here. I think that'll be enough. And we don't have to go up very high. Okay, so let's start with this one. This is going to be a line, right? It's got a slope of 1/2 and a y-intercept of 0. So 0, and the slope is 1/2, so up 1 over 2, up 1 over 2. You get a straight line here. It's not perfect, but you get the idea. Okay, the other graph, mother function for square root graph. If you can't remember it, we can draw it again. Put 0 in here, you get 0, 0. Put 1 in here, you get 1, 1. Put 4 in here, you get 4, 2. And so you get this as your graph there. And what we're interested in, of course, is this area in here. And where we're rotating it is over the y-axis. Right? This is the axis of rotation this time. Okay, so I'll write down that second formula that I wrote that was on the first page. And away we go. Volume equals pi. Okay, what are our bounds? Now, you might be thinking that the bounds are 0 and 4, but no, we're rotating over here, over this axis. So the bounds are actually 0 and 2. Right? We got to look on that y-axis. Now, next thing. F of y, we got to figure out our r and our big R and our little r. So remember, big R is from here to as far away as possible, the outer edge. Well, that would be the red line. This is our capital R. And our little r, I haven't drawn this very well, haven't given myself room, but this is our big R, can't even read it. Little r is to the near edge, so little r is to the blue curve there. All right, so for F, that's the big R, that's the line, that's this one. This is my big R. So should I put x over 2? No. Remember, we want to put it in terms of y. So you got to rearrange this so that you have something that says x equals, and then whatever y is. Well, that's easy. Multiply by 2, you get 2y, right? These two statements are completely equivalent to each other. If y equals x over 2, then x equals 2 over y, and that's perfect. We can now put 2y in for our f function, and of course, we have to square it. Minus. Okay, g of y is a little r. That's the blue function. Well, wait a minute. The blue curve is this one right here. But again, we need to rewrite that so we just have x equals. How would you do that? You'd square both sides, and you'd have x equals y squared. So that's what you're going to write in for here. You have y squared, and then you have to square it. Okay, so let's simplify that. 2y all squared is 4y squared, minus y squared squared is y to the 4th, and we're going to integrate this. Oh good, not as bad as last time. V equals pi. So 4y squared, it's going to be 4y cubed over 3 minus y to the 5th over 5. From 0 to 2, the 0 is going to be lovely. We just have to plug 2 in here. So pi, plug 2 in there. 2 cubed is 8 times 4 is 32 over 3 minus 2 to the 5th is 32 over 5. And then minus, you plug 0 in here or here, it doesn't matter. You're getting 0. It's going to happen often, but of course not always. Anyway, all we really have to do is 32 over 3 minus 32 over 5, so common denominator is 15 again. Multiply by 5, top and bottom, you get 160. Multiply by 3, top and bottom, you get 96. And if you subtract there, 160 minus 6 is 64 times pi, 64 pi over 15. And we are done. So there you go, everybody. You now know the disk method and the washer method. Next day, the shell method. Take care.